In this part, we'll look at Monte-Carlo Tree Search, otherwise known as MCTS. Monte-Carlo Tree Search is an online planning algorithm. We'll define this difference between online and offline planning later. Monte-Carlo Tree Search is a simulation-based planning method, but unlike standard Monte Carlo simulation, it constructs a tree that helps us prioritize more favorable moves in those simulations. It's been key in many multiplayer game solutions in artificial intelligence, and in fact it was crucial in DeepMind's AlphaGo implementation that beat Lee Sedol in 2016. In this module we'll lay the foundation of MCTS for single agent MDPs, and then we'll look at the multi-agent case later. By the end of this part, you're expected to be able to explain the difference between offline and online planning for MDPs, apply Monte-Carlo Tree Search to solve small-scale MDP problems manually, and to program MCTS algorithms to solve medium-scale MDP problems automatically. Should be able to construct a policy from Q functions that result from MCTS algorithms, and integrate multi-arm banded algorithms, including UCB, into Monte-Carlo Tree Search algorithms. And finally, be able to compare and contrast MCTS to value iteration and temporal difference learning that we've seen earlier. So we've seen value iteration and temporal difference learning so far, and these two work well in certain situations. However, for value iteration, well, firstly that's model-based, so it requires a model to learn a policy, but also it learns a policy somewhat exhaustively. And by that we mean that it learns a policy for every possible state in the MDP. If we have a lot of states in an MDP, and we don't need to explore a lot of those states in order to solve our problem, we might waste a lot of time solving using value iteration when it's completely unnecessary. In temporal difference learning, well, that also learns a policy, but that tends to only really work well for very repetitive tasks where the plans look very similar each time, or in situations where we have a huge amount of computational resources and time available before we learn, and we can explore a lot of different states and actions. That's usually not the case for most people. It's usually only the case for a certain set of organizations in the world that have access to such computational power. So value iteration and temporal difference learning are both examples of offline methods in which our policy pi is trained in advance and then we're using it. So the application of an offline method looks like so. We first train our policy pi, and then at execution time, when we're in state S, for example, we take the action that the policy says we should take in state S, and we end up at a new state T. We then take policy from T, end up in state U, etc. In this case here, it's called offline because all the hard work is done offline coming up with the policy. In online planning methods, a lot of the hard work is done online. The planning is done immediately before action execution, and often action execution and planning are interleaved. So instead, it looks something like this. We're in state S. We then delegate out to our planner, our online planner, which we'll call P here, which will give us a recommendation for what action to execute. Let's say that's A. That will take us to state T. At state T, we then plan again using our planner from state T, and it will tell us what it thinks is the best action from state T, which might be action B, etc. So we can see here the difference is that the hard work of doing the planning is online rather than done a priori beforehand. The advantage then of online planning is we're only planning for these states that we actually visit. Whereas in offline planning, we have to plan for states that we will never visit in execution, but because we don't know that beforehand, we have to plan for them anyway. In online planning, no pre-training is required, so therefore we never plan for these states. Although, as we'll see later on, some pre-training beforehand can improve our online planning as well. The disadvantage is that we need the computational resources and the time online to use online planning. So that means we both need computational resources to run the planner, but also that we have the time to pause and do the planning in between each action execution. In very time-critical domains, often this might not be a good assumption. So how do we do this online planning? Well, algorithms such as blind search algorithms, A-star search, real-time A-star search, using Monte Carlo simulation, they're all ways that we can do online planning by simply executing the algorithm and then selecting the action that it says is the best. Before we got onto Monte Carlo Tree Search, let's first look at the background of Monte Carlo simulation more generally, because Monte Carlo Tree Search is just an instance of Monte Carlo simulation. In Monte Carlo simulation, what happens is that we're at a state S, and we have to choose between a series of potential actions. At this state, what we want to learn is the Q value, QS, for each of these actions A, B, and C. In standard Monte Carlo simulation, the way to solve this is quite simple. All we do is look at the actions that we have and run many simulations from the resulting states of what would happen if we applied action A, if we applied action B, and if we applied action C. Run many random Monte Carlo simulations and then look at this point the average reward we would receive having played action A, B, and C. We would then just simply select the action that has the highest average expected reward. It's quite effective and it's remarkably general, but the issue is that we waste a lot of time exploring unfavorable actions. For example, if a lot of the early simulations of C are remarkably bad, we could potentially think about not simulating that as much as A and B, which look more promising, much like a multi-arm bandit algorithm does. But another problem is not just selecting these actions for simulation, but a lot of the actions that we do in the future. At each one of these simulations, we have to select an action to simulate, and we might spend a lot of time exploring unfavorable actions later in these as well, when we could focus on future trajectories that look more like the type of actions we will choose in the future. Monte Carlo Tree Search is one way to try and mitigate this problem. One more piece of background before we get on to Monte Carlo tree searches, and that's Expecti-max trees. MDPs can be represented as Expecti-max trees. An Expecti-max tree looks like this. At the top we have our initial state, and from the initial state we have the actions that could be chosen from the initial state, in this case A and B. And then we have the probabilities of the different outcomes of choosing those actions. So in this case here, action A can have two potential outcomes, T and T prime, with the respective probabilities here. The important thing to note here is that the circles with the text in it represent the states where the agents must choose an action. The arcs in between these two represent the actions. The filled in dots represent what we'd say are choices made by the environment. And by that we mean that there is some randomness in the outcomes of the actions here, and we model this as saying the environment chooses what the outcome is going to be, but it chooses it based on the probability distributions we have here. Once we choose action A and we're in state T, we might be able to then choose action C to go here, and similarly if we choose B, take this outcome, we could choose D or E. The reason these are called Expecti-max trees is because to optimize them, you need to pick the action that maximizes the expected return of the tree, which is the same criteria we use to solve an MDP, the Bellman equation. We can represent any MDP as a possibly infinite tree. These trees are far too big to represent and visualize on a slide, but we're going to use this idea that MDPs are Expecti-max trees in order to help us understand and construct the Monte Carlo Tree Search algorithm for single agent MDPs. So let's look at Monte Carlo Tree Search now. In Monte Carlo Tree Search, the goal is the same as in Monte Carlo simulation. We have a state, initial state S, and we're trying to figure out what the value of every action is from that state in order that we can select that action and execute it and see where we end up. In Monte Carlo Tree Search, we maintain a tree structure that helps us determine which actions are more favorable to explore. This tree structure is constructed in an iterative manner following 4 steps. We do these 4 steps repeatedly until we run out of time, given some time budget to the MCTS algorithm. For this reason, MCTS is called an anytime algorithm. Given a certain time budget, it will return an answer. The more time it's given, usually the better the answer is. But what are the 4 steps that are followed in this iterative manner? The 4 steps are as follows. First is the selection step. In a selection step, we select a node from the tree that we want to explore. Second step is the expansion step. In this case, we take one node that's yet to be expanded and we expand it by exploring one of its actions. Third step is simulation. From the expanded node, we do a Monte-Carlo simulation that goes all the way to a terminal state. We add up all of the rewards that we get along that simulation and return. Then in the fourth step, we backpropagate that reward to the root node. Let's look at how these 4 steps iterate to construct a tree and how that can be useful. So the first thing we have to do is select. So if this is a new Monte-Carlo Tree Search from state S, we have just one node, which is the starting node. We're going to call it S0. We have to select a node to expand. That node always has to be currently not fully expanded, which means not all of the actions that are available from that node have been explored. In this case, obviously none of them have, so we have to select it, and that becomes our selected node. We then go to the expansion step where we have to expand our selected node. We expand by selecting one action that has not been expanded from this node. In this case, there's none of them. So we select any one, and we'll say it's going to be action A, and one outcome from that state. This brings us to a new state here, and that's our newly expanded state. From that expanded state, we run a complete Monte-Carlo simulation down to a terminal state. This Monte-Carlo simulation can be completely random actions, or it could follow some heuristic that you might have to ensure that you get good simulations that are realistic simulations of behavior. We sum up all the rewards that we received along this simulation, and we will call those cumulative sum G, and then we discard the simulation itself. And we assign this G by calculating the average reward that we've received from this node so far. Of course, it's only going to be G because this is the first time we've done it. We then backpropagate this value up the tree to here and calculate the average reward we've received from state S as well. That's one full iteration of our MCTS loop. We then have to do a second iteration. Again, we have to select a node that has not fully been expanded before. And let's say there's one other action that we could possibly select here. That's action B. We select it and choose one of the outcomes of B, which leads us to a note, and expand it. We do one simulation down to a terminal state, get the reward G, we remove the simulation that we did, and then we backpropagate that value by calculating the average reward we've received from this node and backpropagating that back up to step S0. So that gives us 2 complete iterations of the MCTS algorithm. What happens in the third iteration? Well, again, we have to do our selection step, which selects a node that is not fully expanded. Our initial node, S0, is fully expanded now. We've explored both possible actions, A and B. So we have to select a new node to expand. How do we do this? We do this by traversing down and making a selection between action A or B. How do we select which action? Well, we could do it randomly, but a better way to do this might be to select an action using a multi-arm banded algorithm. That way, if action A is shown to be more promising than action B, we will select action A more often in our selection step than we will action B. We'll see in a minute why this is important. So let's say we do select action A, we select action A, we come down to our outcome here, which is a node that is not fully expanded. Now what we could do is also expand one of the unexpanded selections from A here, or we could take this one as well. It's entirely dependent on what our simulator gives us. If it gives us back this node, we expand that. If it gives us back this node, we expand that. For simplicity, let's say we got this node that we've got here. Now we have to apply the expansion step on that, which means choosing an action that's available from this node here. Let's say that there's two more actions here, C and D. We're going to choose action D. That will take us to some particular outcome of action D. From this one, we do our simulation again till we reach a terminal state. We take all the rewards from that, we feed them back to this step here, and then we back propagate our rewards up our tree, calculating the average return for this leaf node, the node that we've expanded, but also our original node as well. And again, we get rid of all the simulated information, and that's the tree that we have so far. Let's just do one more iteration of this and see which one we're going to choose next. So we have to select another node to be expanded that hasn't been fully expanded before. Again, what we do at each step is we use a multi-arm banded algorithm to decide which action we're going to select. In this case, action A might have been more promising, but because our multi-arm banded algorithm has some randomness in it, we might choose to take action B, in which case we would expand this node. Or again, we might choose action A in this one here. If we reach this node here, we would have to expand it again, because as I said, there was two actions available from that, C and D, so we would have to expand C. Do the simulation, backpropagate the reward. So what we'd see now is that we'd have the Q values for actions C and D from this node here would be the average reward we've received from executing C and D, which would just be their two simulations. The Q value of A would be the average reward from the two simulations we've done so far, and the Q value of B would be the reward we received for that simulation. What we do is we progressively expand this tree until we end up with something that's a little bit more sophisticated than what we see here. Let's have a look. So now we have a slightly more expanded tree. It's still one that's tiny compared to one that we would expand if we use an algorithm to do this. But I just want to go through and do one more iteration of these 4 steps, particularly the selection step, to illustrate how this works. For the selection step, we start always at the root node. From the root node, we first look at whether the node is fully expanded. That is, have all the actions that are possible from this node been explored at least once? If not, then that's the node we choose to expand, and we move on to the expansion step. If they have been fully expanded, we use a multi-arm banded algorithm to choose between our actions based on the Q values that we have for these actions so far. If we used a multi-arm banded algorithm here, we might choose action A and end up in this outcome here. And then again, we look at that node. Is that node fully expanded? If not, that's the node we choose to expand. We go to the expansion step. If it is fully expanded, again, we use a multi-arm banded algorithm to select. In this case, we would use a multi-arm banded algorithm to select between C and D based on their Q values. And let's say, for argument's sake, we choose D and end up with this outcome here. Is this node fully expanded? Possibly, maybe there's a third action that's available from here, but I'm going to say this action, let's say this action is fully expanded. We have to choose between action A and B. We're going to choose a multi-arm banded algorithm again. And in this case, we'll choose multi-arm banded algorithm, and it's going to choose action A. And let's assume we end up finally down at this outcome here. At this point here, we come to an action that's clearly not fully expanded because there's been no action expanded from it. So here was where we'd have to apply our expansion step one more time, choose one of the actions that's available, say it's action G. The simulator would choose one of the outcomes. That would be our expansion step. Then we would do a simulation, get the rewards from that simulation, which we would say might be rewards G. Forget about the simulation itself, we discard that. We then do backpropagation. How does this backpropagation work? We follow back up the chain of all the parents that we've done so far, and at each point we update the average reward that we have received from that node so far. We just do this by calculating the average in a cumulative way. So we would update this node, backpropagate to this node, here, and here. So what we can see we're doing here is we're progressively building a tree. Each time we go through one of these iterations, we expand one more node, we run one more simulation, we gain one more bit of information for all of the actions that have been selected on the path that we chose. The key for why Monte-Carlo Tree Search works so well compared to Monte-Carlo simulation is in the tree data structure. At each point here, when we use our multi-arm bandit algorithm to select an action, we're inherently prioritizing more promising actions and exploring those more. But it's not just at this first step we apply the multi-arm bandit algorithm. At subsequent steps we apply them as well. So even in the second step here, we're choosing to apply actions that are actually going to be more likely to be chosen in the future if we did select action A. And so the way you can think about a Monte-Carlo tree search is that the tree is building up information that allows us to guide the early parts of our simulations by only choosing the more likely actions that will occur in the future. The second reason why we find it very useful is because when we eventually run out of time, we have to make a selection for our action. For argument's sake, let's say that A remains our best action and we select it. We then execute that action. Remember, this is an online planning algorithm. We execute that action and we go to a new state. If we go to that new state, the likelihood is that we have actually explored that state somewhat already. So let's assume that we execute action A. In this case, it's going to take us to this state here. What we do is we discard all of the information about the options that we didn't discover. And now we have to make a choice from this new state as to what the action should be. But as you can see, we've already built up part of the tree for this state already using the simulations from the previous step. Whereas in standard Monte-Carlo simulation, once we've chosen our action, all of the previous simulation we've done is gone. So we've already constructed part of our Monte-Carlo simulation for our new action after we've executed it. Therefore, we keep that part of the tree and we use that in the very next step. So this building of the tree is key to what makes Monte-Carlo Tree Search an improvement over Monte-Carlo simulation. It's guiding more promising simulations early, and it's allowing us to keep some of the hard work we've done in one step and use it in the next step. Now let's go through an example of MCTS in which we apply the selection, expansion, simulation, and backpropagation steps in more detail, and that will fill in some of the gaps that we missed on the overview slide. So here we have a tree that has been partially expanded. In this diagram, the letter at the top of a node represents the name of the state and represents the number of times this state has been visited, and these labels here represent the action names. What we have to do is select a node to expand next. Now let's assume that A and B are the only two actions that are possible from state S. We then use a multi-arm bandit algorithm in order to choose which action. Our multi-arm bandit algorithm is going to choose the A action here, and our simulator is then going to choose the least likely outcome here, and we're going to result in step T. At this point, the state T, or the node at state T, is not fully expanded, so this is the node we're going to have to choose to expand. When we expand it, we choose one random action. We're going to choose an action that's called F, and the outcome that's chosen, let's say there's only one possible outcome that's chosen, it's going to lead us to a state that we're going to label as Y. That's our expansion step finished. We've expanded, we've got a new state Y. Now we have to do a simulation from that. We're going to run a simulation all the way down to a terminal state, take the cumulative reward that we received over that state, and propagate it back. Now let's for a minute assume that the final reward we received was 31.25. You'll see why it's that reward in a minute. We have to discard our simulation and start our backpropagation step. In the backpropagation step, we're going to update our new state Y state T, and state S. All of these that were on the path that we used to select this node. So what we have to calculate is the value Q of Y for the first action that we did in our simulation. Now we throw away all the information about our simulation, except for the rewards that we received and the first action, so that we can actually calculate this. In this case here, we need to calculate the average reward we've received every time we've played action G in state Y. We've only done this once, so we can just calculate what the reward is. Now, if you recall, the reward we received at the end of our simulation was 31.25. However, what we have to remember is that reward should be discounted. If we're in state Y, let's assume, for example, that our simulation was 3 steps long and we received 31.25 at the terminal state. That would mean that our reward is going to be gamma squared times 31.25. In this case here, it's gamma squared because our simulation was 3 steps long. After the first step, that's our immediate reward, that's not discounted. The second step is discounted by gamma, and the third step by gamma squared. Now if we assume that gamma is 0.8, our expression here simply becomes 20. Look at that, a nice round number, what a coincidence. So our value of choosing action G in state Y would become 20. That's the average reward we've received so far, just that one simulation we've done. So we would add this to our Q table as 20. So we've backpropagated that first node. Now what we've got to do is backpropagate that to the next node. Let's look at it. In this state here, we need to calculate backpropagate QT of F. To calculate that, we're going to use our Monte-Carlo reinforcement learning update rule. Therefore, the update's going to look something like this. Q of TF is equal to the old value of Q of TF, which we look up from our Q table over here. Okay, that's 0. That's easy, isn't it? Plus 1 over the number of times we visited this state, which is 2 now. It was 1 previously. This is the second time we visited it. Plus the reward we've received. I haven't said anything about a reward here, so we're going to assume that's 0. Plus our gamma times G. Our G here, remember, was 20, our reward from our previous step, minus the old value. And if we do this calculation in our head, we get the nice round value of 8. So the new value of Q of TF becomes 8. So let's get rid of the old value, burn the new value here. And finally, we have to do state S. What we need to calculate in this final step then is QS of A, because A was the action that we selected in our selection step. I'm not going to write out the entire formula again here, I'm just going to fill in the details, and you can look at the notes if you really need to refer to them. But Q of S of A is going to be equal to the old value of QS of A, which if we look up in our Q table over here is 18, plus 1 over the number of times we've executed that, so it's 10, multiplied by the reward that we've received. If we execute QS of A, in this case here, we received reward of 6. We must remember to add the rewards that we receive along the tree, not just the rewards we receive at the end of simulations. There are intermediate rewards we have to consider. 6 plus gamma 0.8 multiplied by G, which is our cumulative reward. Now our cumulative reward, remember, is going to be the reward we received from Y discounted again. So therefore it's going to be 0.8 times 20. So we're discounting the reward we received of that as 0.8, 0.8 and back up again. minus our old value QS of A, 18. And if we do the calculation of this, what we'll end up with is 18.08. At this point then, we would update our Q function to give 18.08 for our value QS of A. So the number of backpropagation steps we do is always going to be equal to the number of actions that we selected in the selection step plus 1, the expanded action. If you read a lot of articles on MCTS on blogs, most of these are applied to situations where there's only a reward in the terminal state and there is no discount factor. But from a more principled manner, we have to remember that there can be intermediate rewards and there usually is a discount factor in our problem. So we have to factor that in. An important part of any Monte-Carlo Tree Search algorithm is the multi-arm bandit algorithm we use in the selection step. Because after all, this is going to be the thing that selects which actions we should prioritize and focus on in our simulations. It has a really big impact on the overall success of the Monte-Carlo Tree Search algorithm. Upper confidence trees, or UCT, is the name of an algorithm that combines Monte-Carlo Tree Search with the UCB1 multi-arm bandit algorithm, upper confidence bounds, or at least a slight modification to UCB1. In UCT, during the selection step, when we encounter a node that's already been fully expanded and we have to select an action in order to progress down the tree, we use the following expression in order to select an action. Recall that from the UCB1 algorithm, n of s is the number of times the state S has been visited, and ns of A is the number of times that action A has been sampled from this. The UCT selection adds an additional parameter CP, C of P, which is the exploration constant. CP can be increased to encourage more exploration and decreased to encourage less exploration. In this algorithm, if QS of A is in 1 and CP is equal to half, then in two-player zero-sum games, UCT converges to the well-known Minimax algorithm. If you're not familiar with what a Minimax algorithm is, don't worry about it for now, but it's an interesting theoretical result. Experiments show that the UCT algorithm is a remarkably robust algorithm for Monte-Carlo Tree Search and Monte-Carlo simulation. It seems that, like in multi-arm bandits, the UCB selection rule is a very good rule that's robust to change, robust to drift, and learns very quickly. For that reason, UCT is probably the most well-known and most well-used Monte-Carlo Tree Search algorithm, especially in two-player games. Here's an example of an MCTS tree that's generated for our simple Gridworld example. It's been cut off after 7 levels of the tree in order to avoid too much information being printed. Now, it's far too large to inspect the tree in any particular detail, but there's 2 things I'd like to just note on this tree here. The first one is what it visualizes. It includes the outcomes, or the probability of outcomes from the model. Remember, we do know these probabilities in the Gridworld model. Even though our MCTS algorithm doesn't use them, I've put them in the visualization here. Looking at things like the count of the number of times that a node has been visited, we can see that this node's been visited many more times than this node because this outcome is more likely than this outcome. So our MCTS algorithm is selecting the action, but our environment is selecting this as a more likely outcome, around about 10 times more likely than this one here. But the second thing that I want to point out here is just a weakness in the simple implementation that I used to generate this, is the repeated states. Here we have the value of a state and its name, value of state 0, 0. I select an action left and I end up in this state again. And then I select an action left and I end up in this state again. Then I extend left and I end up in this state again. We can see that we visit repeated states quite often. This means that we spend a lot of time evaluating the values of states that we've already visited several times. Now that can be useful. However, we might find it more useful if instead of continuing to expand on this, we don't expand states that we've already visited before, and we simply use the information we already have, our Q values, to return an estimated value of that state as part of our MCTS. This means that we can avoid visiting the same states over and over on the same path. Of course, we want to visit them over and over for sampling purposes, but not necessarily on the same path here, because it's not really giving us any useful information. This will hopefully improve our simulation and improve the outcomes that we get by allowing us to use that time to focus on newer states. So let's look at how our Monte-Carlo Tree Search algorithm learns a Q function, and let's look at some of the convergence properties of it in a single agent MDP. So here we have our hopefully now familiar simulation environment for learning in Gridworld. Unlike the Q learning and the value iteration one, we're not going to look at iterations or episodes and how it works, but at time. On the top here, we can see the time because we finish MCTS after a time budget. In this case, we're just going to look at 1 second of execution. At the start, our Q values are all initialized to 0. And if we step through it after an iteration, we can see that we get some information in our Q function here. And after a certain number of seconds, say 0.05 seconds here, we're starting to get information about our problem. What's important to note here is that the values start becoming filled from the initial state out, which is unlike value iteration and Q learning where we see our values getting filled from the rewards out. Another thing we can see here is after these few iterations, the early values that we learned are somewhat noisy. So we can see here, it's not too bad actually saying that going left is similar to going up and going left here is better than going up. This is because in early simulations, we're basically taking random actions, and a lot of the early simulations are probably more likely to land in this state because it's closer to the initial state than the good state. Therefore, we're getting some negative rewards early on. And then when we start learning a bit, we get a bit more positive rewards. So there's quite a bit of variance in these early episodes. Nonetheless, if we play through our simulation, we can see that we learn more and more information as we go. At the moment, not so good, but by the time we get to the end of our simulation at 1 second, you can see here we've gotten some reasonably good information about what should happen. Remember, the only decision we need to make in an online environment is what to do next. If we start off in this initial state here, all we have to do is choose our first action. We can see that going up is our best Q value, so we would choose that. If we were successful, we would go to this state and we would replan again. But you can see because we've kept part of our tree, when we come to plan again, we've already got some pretty good information to go on. It already tells us that going up is the next best action, then going right would be the best action after that, then right again, then right into the goal state. So as we throw away part of our information about making this choice here, we'd move into this state. We already have some fairly good information about what we would do next. Like Monte Carlo reinforcement learning, if we're using a Q table in order to represent this, after an infinite amount of time, Monte Carlo Tree Search will converge on an optimal Q function. However, the true value of using MCTS is really seen when we're in a situation where there's only a limited amount of time to do planning that's available. In some of my experience, for example, looking at planning for disaster management, MCTS was pretty much the only feasible technique that we could use in some of these situations. We've looked at things like deep Q learning and Q learning with abstract Q tables. The issue in those situations is that we have a huge state space, much larger than, for example, the game of Go, which is known to have a massive search space and a massive state space and makes it challenging. In the situations that we're looking at, the state space is much larger than games like Go, and each possible case that we encounter is so different from ones that we've seen before that anything we did offline was more or less worthless because we were unlikely to ever encounter similar situations when we looked at it later. That's not to say that you couldn't apply things like Q learning or deep Q learning to situations like that, but the amount of computational power you would need and the amount of time you would need access to that computational power is prohibitively expensive for most organizations, especially organizations like university, and is reserved only for companies that have millions of dollars of hardware that they're able to dedicate to this. So MCTS becomes a valuable alternative doing online planning that allows us just to explore the states that are relevant to make decisions for us at particular times. In the demo on the screen now, we see an example of Monte Carlo Tree Search playing the game Freeway. In the game Freeway, the idea is to get the kangaroo character that you can see at the bottom across the road to the other side without being run over by a car. Here we can see the MCTS implementation trying to play Freeway, but doing reasonably poorly. On the one hand, it's doing one thing well. It's not getting run over by cars, at least not very often. But on the other hand, it's not getting to the other side. Why is this the case? Well, it manages to avoid getting run over by cars because the negative reward of being run over by a car is fairly short term. If you make a move and you step into a lane when a car's coming and it runs you over, you reach a terminal state, you get a strong negative reward for it, and you will learn very quickly that that's not an action you should select using your simulations. The issue with this is that it never reaches the other side because the positive reward is so far away. It requires so many steps to get to the other side that at the start of the simulation, random simulations of going up, down, left and right never make it to the other side of the road. So it never gets that small positive reward for reaching the other side of the road. So in other words, it fails because the length of the plan to get to the other side of the road is so unlikely that our MCTS algorithm simulations never encounter it. In the small time budget it's got, it's only doing enough to encounter short-term negative rewards, being hit by a car and learning how to avoid them, and never reaching the other side. Let's look at another example now of MCTS playing Super Mario Bros. These lines that are sort of projecting out of Super Mario are, I think, the promising moves according to the MCTS tree being visualized by the developers. It plays Super Mario Bros. A lot better than Freeway because there's so many short-term rewards available. Therefore, it doesn't have to simulate very far in the future to figure out where the short-term rewards are. So, MCTS is a weakness. So a weakness of MCTS is that if the rewards are very far in the future, it's unlikely that we'll encounter them. It's also the case if the rewards are very sparse, that is, they don't happen very often, our simulations won't see them very much and they won't have much of a signal to go on. On the other hand, if the rewards are quite easy to access, then it will work quite well. But this is a similar weakness that exists in temporal difference learning, for example. If rewards are very far in the future, our simulations that we're performing are unlikely to come across them, and therefore there'll be very little signal to go on. And in future, we'll look at some of the ways that we can get around this and improve our learning by injecting some domain knowledge. In this part, we looked at Monte-Carlo Tree Search, an online planning algorithm for MDPs. By online, we mean an algorithm where the planning and the execution are interleaved. Monte-Carlo Tree Search is an instance of Monte-Carlo simulation, but it's one that incrementally builds up a tree that helps us to prioritize more favorable moves. It consists of 4 main steps: selection, expansion, simulation, and backpropagation. We looked at the UCT algorithm, upper confidence trees, which uses the well-known upper confidence bounds, UCB, as a multi-arm banded algorithm in the selection stage of Monte-Carlo Tree Search. Monte-Carlo Tree Search is particularly effective in massive search spaces when we don't have a lot of resources or time available beforehand to explore states, but we do have some computational time online in order to explore those states that are most important. Next up, we're going to look at situations like the Freeway example, where there's a very sparse reward signal. It's quite weak and we don't get a lot of information or feedback from our algorithm as to which actions are most promising. What we need to do in those situations is inject a little bit of knowledge to the algorithm that can help it find a good solution.